Thank you. Yeah, I'm Kerstin. I'm working for Xing. We are building a social networking site for business professionals. And I'm going to talk about asynchronous messaging. So let's have a look at machine-to-machine communication. This is part of the distributed infrastructure behind Xing.com. If a user is interested in information about a particular event, maybe a conference, their request hits our events application, which can easily serve data like the conference location or the conference description. But in order to display a proper list of attendees, it needs to know their names, their job titles, their companies, and so on. And this data is not owned by the events application. It's living in the core application. So we have to use our internal REST API to fetch this data and display it to the user. This is actually a good use case for REST, since we are fetching data that we are immediately going to display. Now, what if you simply want to inform another application about something that has already happened in your app? Then you might actually be better off using asynchronous messaging instead of REST. For example, AMQP. AMQP is the Advanced Message Queuing Protocol. It's an open standard that allows you to exchange messages through some middleware. We call this middleware a message broker. Message brokers are available in different implementations. There are even some cloud services offering it. So if you have a small pet project deploying to Heroku, you can still use AMQP through some of those services. In addition to the message broker, you have a producer or publisher that's sending messages and a consumer that is receiving messages. Producer and consumer are some of your applications. It might be the same application on the same machine, but it can as well be different applications running on different machines. And since AMQP offers a high degree of interoperability, they can run on totally different technology stacks. Okay, if the producer sends a message, this message ends up in a so-called exchange on the message broker. A message has a payload, which is basically the data you want to transmit to the other application. We use JSON to format it. And each message has a routing key. A routing key is just a string normally associated with the purpose of the message. And the exchange uses the routing key in order to find out what to do with the message. Dependent on the routing key, it puts the message into some message queue from where it can be consumed by the consumer application. Now let's look at some use cases. If a user deletes their account on our platform, we remove their data from our core application. But other applications have data about this user as well. So we send an AMQP message with the user ID as a payload and a routing key users deleted. The consumer applications might be the events application or the job market or something else. The consumer learns about the deleted user and can clean up their database. The publisher of the message doesn't really care what the consumer is doing with the information about the deleted user. So it sends a message and immediately moves on to other tasks. It doesn't expect or need any kind of response. A similar use case is caching. Some of our applications cache user data for performance. Now, if the user updates their data in the core component, we send another AMQP message with a routing key user updated to inform the consumers about the update, and they can, for example, invalidate the cache. Those messages have the user ID as a payload and maybe the fields that have been updated, but we do not include the updated data. There are basically two reasons for that. One is that this data might already be outdated when the message arrives in the consumer. The other reason is that we generally try to keep the payload small in order not to overwhelm the broker if there are many messages. If the consumer happens to need the updated data right now, they can always follow up with a REST request. And our REST API always returns the most recent data to the consumer. So in those examples, we have one producer publishing the messages and several consumers. Events, application, job market, they all need to learn about user updates or deleted users. So the exchange takes the message and puts it into several independent message queues from where they are consumed by several independent consumer applications. If a consumer is down, the message stays in the queue until it's up again, and the producer is not affected. We can even add additional consumers, and all we have to do is set up another queue in the message broker, and the new consumer is good to go. We do not have to touch the producer's code. Now, instead of having one producer with several consumers, you can as well have several producers sending messages with the same routing key to one consumer. For example, for tracking. We used to consume a quite expensive third-party API and wanted to track our usage. Unfortunately, it was consumed from several different applications. Of course, every application can track their own usage of the third-party API, but this would leave us with the annoying task of combining all this data. So what we did instead is have every application send an AMQP message whenever they request the third party. And we set up one consumer receiving all those messages. It wasn't very smart. All it could do was increment a counter for every message it received. But this allowed us to have a centralized tracking for something that was happening across multiple applications. In a similar fashion, you can send data to logging or monitoring systems from all your applications and combine it there into something meaningful. Now we have seen several producers sending to one consumer and one producer sending to several consumers. So you might come up with the idea of having several producers sending to several consumers. Technically, this is entirely possible, and QP is fine with it. Still, you better think twice if you really want to do it. Sooner or later, you might have to do changes to the format of the message payload, which basically is an API change. So if you're doing a breaking change, it might be really hard to coordinate that between multiple producers and multiple consumers. Okay, the use cases we have seen so far had something in common. Basically, the producer informed the consumer applications about something that already happened before in the producer. In difference to that, you can as well allow the producer to trigger something to happen on behalf of the producer in the consumer. For example, you can use AMQP in order to run time-consuming tasks asynchronously. If a user uploads a new image to our platform, we have to create thumbnails in different sizes and upload them to a cluster of asset servers and so on. And this is taking way too long for a user-facing request. So we simply don't do it in the user-facing request. Our user-facing request sends an AMQP message about the uploaded new image and immediately returns to the user, informing them that their image is going to be processed. A consumer receiving that message is actually doing the heavy lifting and the time-consuming things. You might even set up a dedicated worker machine that is only consuming those messages. So if there is a sudden spike in image uploads, the only thing that slows down is the processing of other uploaded images, while the rest of the platform is not affected. If you want to speed things up a little bit more, you can set up several worker machines running the same consumer code, consuming messages from the same queue. So whenever one of them has free capacity, it fetches the next message and processes it. In this case, you cannot rely on the order of the messages. So a message that was sent first is not necessarily consumed first. Still, it's a nice way to scale your system, especially for migration purposes. Xing recently switched the format of the user images from rectangular to square images. And in order to prepare for that switch, we had to create image files, squared images, for every user that has a picture. This could be quite time-consuming, so we decided not to do it in one long-running script migrating users sequentially. Instead, we built a migration script that sent an AMQP message for every user that has to be migrated. We set up a bunch of consumers consuming those messages, and they actually did the real migration. The consumer code for that is very simple. It doesn't know anything about running this migration in parallel of several machines. So all a consumer needs to know is how to migrate one particular user at a time. There are more advantages to running a migration like that. Think of a long-running migration script that is really doing the heavy task. It's going to crash, you have to restart it, make sure it picks up exactly where it crashed, and this is most likely going to happen several times, keeping you busy. Our migration script was only sending the AMQP messages, so it was finishing quickly and saved us from all this extra effort. Still, the processing of all those messages took quite some time. At least we had to create quite a number of images. So users were still hitting the old implementation, and some of them actually uploaded new pictures while our migration was still running. So we've implemented into the old image upload code that it also sends our migration AMQP message whenever a user uploaded a new picture. So this user automatically ended up in our migration queue again, independent of the fact that it might have been migrated before, which basically ensured that at the end of the migration, we had squared versions of the most recent user images. So basically, we used AMQP to keep the old system and the new system in sync, while the users were still making modifications through the old system. You can as well set something up that kind of works the other way around. Have your new system send an AMQP message to a consumer that updates your old system. If you do this, your systems stay in sync even after you have switched on the new one, which is basically nice just in case you have to switch back to your old system if there are some issues with the new one. So if you're running a big migration like this, you really want to test it. A while ago, we have built a new application for the user profiles on our platform, which is where the users store their CV data. And this application receives quite a lot of traffic. So we wanted to be sure that our new application could handle this traffic as well. While user requests were still hitting the old implementation, this triggered an AMQP message about every request it received. A consumer receiving those messages could follow up with a so-called shadow call, making the very same request to our new implementation. The users were not affected by this. In the beginning, we dropped most of the messages, and then we slowly increased the percentage of messages resulting in a shadow call until we finally reached 100%. So we could be pretty sure that our new application would be able to handle all the traffic it would get after going live. So besides the traffic, this also gave us a nice opportunity to test our application with live data. So instead of thinking about all the edge cases that might occur in the application and that we may want to test, we were basically routing live traffic to the application. And if you do this for, say, 2 weeks, most likely hit all of the edge cases that are present in your data. And if our new application wasn't able to handle those edge cases well, we would see something in our monitoring or logging and could fix all those bugs before going live with the new application. Users didn't notice anything because they were still served from the old system. Yes, to sum it up, asynchronous messaging can be a nice way to run tasks asynchronously or in parallel without you having to use any advanced programming techniques, because all the magic is happening through your messaging setup. And it also allows you to decouple your applications quite a lot. So if you need to add or remove a new consumer, you don't have to touch the producer's code, and vice versa. If a consumer is down, the producer doesn't even notice. Same if a producer goes down, the consumer doesn't notice. So basically, you can use it for a lot of decoupling, which gives your overall system a lot more stability. Yeah, that's it. Thank you very much. If you have any questions, I'll be around for the rest of the day.
Thank you.